Thanks for the introduction. Good morning, everyone. So today I'll be sharing our work showing how ventral string neural manifolds support human visual robustness. The human visual system is incredibly resilient in a noisy world, but deep neural networks, although they have incredible performance on visual tasks like image classification, they are shown to be surprisingly fragile. So for example, even tiny image perturbations that are invisible to human eyes can trick them into mistaking this dog for a cat. And I can make the noises more prominent so that it is even easier to fool the deep net. But of course, for humans, we would never call this a cat, no matter how large the perturbation is. So how do we humans achieve such resilience? A long line of research suggested a critical role for the ventral visual stream to build more abstract representations along the way. In our own work, which we presented at last year's VSS, we used neural guidance to demonstrate how we can induce robustness in these artificial systems using the ventral stream representations. More specifically, we adopted this dual-head architecture, so asking deep nets to simultaneously perform classification and then align their penultimate layer representation to one of the 7 regions we picked along the ventral stream. And we used the fMRI recordings from the famous NSD dataset. And then we evaluated these models with standard robustness tests that add this kind of noises across different magnitude. And we found that neural guidance from these brain regions lead to hierarchical improvements in model robustness. So this was strong evidence that the ventral stream representations could be increasingly support visual robustness. However, with this previous setup, our results can only say that, okay, the human neural representations are helpful, but we didn't really ask why they are helpful. What's actually superior about them and what properties of these representations might be driving the robustness? So today we're excited to share a follow-up where we tested one influential hypothesis, that is the manifold disentangling hypothesis here as a potential explanation. So the core idea for this framework is that the neural space could be evolving across the ventral stream by pulling apart or disentangling category manifolds. And this disentanglement will naturally lead to robustness. To unpack this a little more, consider a neural state space of a given brain region. When we present an image, say of a dog, the pattern of activity across neurons give us a point in this space. If we show more dogs, and importantly, different identity-preserving transformations of these dogs, we get more points. And these points should trace out a continuous surface in the space, and this is what they call a category manifold. And the same would apply to, for example, the cat category. But in reality, these manifolds could be highly entangled in, for example, the raw pixel space. So it's hard to separate them with a linear boundary. And in fact, we might even, for example, mistake these 2 versions of the same dog as 2 different objects. Now, what our ventral stream does might be doing is to transform these entangled manifolds step by step to become these very separable ones embedded in the final optimal neural space. And then since all these versions of one object are just different points on the same manifold, then in this ideal space where we are able to fully separate everyone, you can see that invariance should not be a challenge anymore. So this framework gives a quite powerful account of how the ventral stream could be solving the invariance problem. And then motivated by this, we here ask whether human neural representations are superior because they form these nicely structured category manifolds. And we approach this in 2 steps. So first, we characterize the geometry of category manifolds in those neurally guided deep nets to see whether they indeed have more desired properties as predicted by the framework. And then we go a step further to ask whether these manifolds are part of what's driving the robustness. Okay, first, what exactly makes an ideal space? So consider these example dogs and cats manifolds. Remember that all that matters for robustness is whether these manifolds can be separated linearly. So intuitively, their diffuseness should be important. That is, if they take up less volume in a space, then it is easier to separate them. But if they're larger and diffuse, then it's just more difficult. So a good space should really have tighter manifolds and thus better separability. To quantitatively measure these manifold properties, we used the recently developed framework called MFTMA, and the first speaker has already given quite amazing introduction to this. I'm going to skip all the math, but given C categories and M image samples from each category, we can extract radius, which is how spread out the manifold is, dimensions, so how many dimensions along which the manifold has significant volume. Combining them, we get the extent that roughly measures overall how diffuse the manifold is. We can also estimate a linear separability across all manifolds in the entire system, alpha, with chance value being 2 over m. So for deep nets guided by higher order ventral stream regions, we should really expect manifolds with smaller extent and increasing linear separability. Okay, so we extracted penultimate representations from those neurally guided models, and then constructed 50 category manifolds, each with 100 image samples using the ImageNet test set. We then subjected these representations to MFTMA, and we indeed found a qualitatively rough trend showing that models guided by higher order brain regions have manifolds with smaller extent and higher separability. And in contrast, the baseline models, so the deep nets without proper neural guidance, had large and diffuse manifolds and worse separability. To quantitatively connect these manifold properties to the model's robustness gains, we first summarized each model's robustness improvement using the difference in area under the curve, so delta you see here, compared to the baseline model. And then compare these to the manifold statistics. So ideally, we should see that models with less diffuse and more separable manifolds should show greater robustness gains. And our results indeed confirm this relationship and showed that these manifold statistics can predict the robustness improvements we saw earlier. Okay, so I've shown that these models do have these desired properties as predicted by the framework. And now we take a step further and ask, could these neural manifolds be what's actually driving the robustness gains observed with neural guidance? Note that in the manifold disentangling framework, it's not the individual representations that matter most, but the overall geometry that determines how separable every manifold is from others. So what this means is that even if I reassign individual points within a category, so moving them around, as long as the overall manifold geometry stays the same, robustness should be preserved. So let's actually consider the previous neural guidance setup, especially this neural alignment loss here. So when we align the model to, for example, V1, this one-to-one mapping between them might just be a way to show the deep nets what an ideal neural manifold should look like. So probably we can get away with just matching every pair of category manifolds. And this is what we did with Manifold Guidance. That basically moves up a level of granularity. So we're feeding the models with only manifold level rather than precise image-wise information. I'm going to skip all the technical details again, but intuitively, we encouraged alignment on 3 aspects, from their position in the high-dimensional space, to size, so the volume of the manifolds, and the orientation by encouraging them to span the same linear subspace. We then used neural manifolds from each of the 7 ventral stream regions to guide the deep nets and assess if we can recover the robustness hierarchy observed before. Okay, let's now take a look at the results. So we again used these standard robustness benchmarks and test the model's classification accuracy across increasing magnitude of perturbation. So first, I'm showing the classification accuracy here for the baseline model. That is the deep net with no neural information at all. As expected, when we increase the perturbation magnitude, we see this decreasing accuracy. But when we apply manifold guidance from V1 and V2, we start seeing some improvements, a tiny bit more with V4. We see additional improvements from the 2 more anterior regions, and then more with the higher order regions. So despite a smaller magnitude, we do see that manifold guidance still leads to this hierarchical improvement. But what's more important here is, for our question actually, is whether this hierarchy is the same as our previous results, because we want to know if manifold structure is what's driving the effect. So we take the robustness gain as AUC, delta AUC here again for manifold guidance, and then bring back the gains from neural guidance, and then compare them. And we see that manifold guidance indeed qualitatively preserve the same hierarchical pattern as we saw before, even though it's only half as powerful. Okay, so with manifold guidance, we basically showed that the structure of neural manifolds alone still carried information enough to drive this robustness hierarchy qualitatively. Okay, to recap, our previous work demonstrated this gradual emergence of robustness across the ventral stream. And today I walked you through a follow-up to ask basically a mechanism question. So what properties of neural representations are responsible for this hierarchy? And we focused on the manifold disentangling hypothesis to show first how neural guidance from higher order regions can lead to smaller and more separable manifolds. And then even guiding models using only manifold structure can qualitatively reproduce the hierarchy. So together we showed that the human ventral stream is superior in part because it is progressively shaping neural manifolds into more ideal forms. But of course, as you can see that we were not able to reproduce the benefits quantitatively. This could certainly be a result of limitation in our methods, which is really just the first order linear approximation of the manifold. But we suspect that finer grained structure within manifolds could also play an important role, and that's what we plan to investigate next, so stay tuned. Okay, finally, a special thanks to my collaborators, my advisor Diane, and our funding source. So our preprint is coming out tomorrow on arXiv, but if you're interested, feel free to let me know and I'll send you a copy. Thank you all for listening, and I'm ready for any comments and questions.
So we have time for questions.
Yes, the hope is really that we can extend beyond those first order linear approximations. The main bottleneck is that we need to integrate these laws into the training of the neural networks, which is we need to accommodate like those batches and to accommodate our computing resources. So if we go for nonlinear, which so for methods like UMAP and other manifold learning stuff, it won't be as easy. It won't be as, I guess, computationally efficient or realistic to realize this. But this is, I guess, a method advancement that we're hoping to achieve in the future. Yeah, thank you for the question.
Got it. Very nice talk. Just a devil's advocate question. So like manifold capacity increases if the exemplars get more tightly clustered around, say, a centroid, but in the limit, do we really want that? Like let's say if your task isn't categorization but subordinate level discrimination, granted the IT measures that we get out of fMRI voxels aren't that tight, so it's beneficial in this range, but would you care to comment on that? Like in a way, it depends on what your objective function is. Like if I want to become a dog expert, I don't necessarily want to throw out all that information.
Yeah. If I'm understanding this question correctly, are you asking if we think that they actually cluster around the centroid that tight? Like, do we think that the optimal condition would be everyone just clustering around the centroid? We don't think so. That's why I had the follow-up project up there. And I think that this could be one of the reasons that we don't see enough improvement in our experimental results, and this is definitely on our next step list. Thank you.
Okay, thank you so much.